Hello everyone, it's me, Professor Aaron Albert, here again with lesson 18. Let's learn some econ. So today we're going to go through and actually fully solve the producer's problem. That's going to begin with defining and illustrating formally the isocost and isoquant curves we saw a couple lessons back. We'll talk about cost minimization in a graph. We'll show how if you change your isocost or your isoquants, that'll change your solutions in a graph. Then we'll show how we go about solving for the cost minimizing output numerically. And then we'll talk about the dual problem. All right. So let's formally define isocost lines as lines that show all combinations of inputs that require the same expenditure. This is kind of like the budget line for the consumers, but firms have costs, not budgets. So first off, let's imagine that a firm's got some L, they've got some K. What are their costs? Then, when you found those, what's the firm's total cost? Answer these to yourself. Well, first note, firms must pay for their labor. If every unit of labor costs W wage dollars, and they have L of them, their total variable cost labor bill would be W times L. Similarly, if they have K units of capital, each costing R, their capital bill would be R times K. Therefore, their total cost would just be WL plus RK. You'll note that if graphed in a labor versus capital graph, WL plus RK is linear, right? Just like Q1, P1 plus Q2, P2 makes a line, so does WL plus RK. Next thing we might ask is, well, how can we find its slope? i.e., at what rate must we trade labor and capital in order to maintain the same level of cost? Think about how we did that before with the budget line for consumers. See if you can figure it out. Well, note we have C equals WL plus RK. We want to know the effect of W on K, so why don't we just rearrange this cost function to be K as some function of L. Once we have K as some function of L, it's pretty easy to find dkdl. In fact, dkdl is just the ratio of wage to rent. So just like before, the slope of y equals P1 Q1 plus P2 Q2 is negative P1 over P2. Wage is the price of the first object. Rent is the price of the second object. Therefore, our ratio of prices is just W over R. Similar to isocosts, we have isoquants. Isoquant is a curve showing the same quantity output. It's analogous to the consumer's utility function, right? Consumers maximize utility, firms maximize quantities, and we want to find all points that make a firm just as happy. Let's assume we've got some Q equals some function of L and K, right? Our inputs are labor and capital, not some other things. And let's assume that labor and capital are combined using Cobbs-Douglas technology. What would our isoquants look like? Well, we can apply our same logic we had before. We got our L, we got our K. We have Cobbs-Douglas, we could have some root LK. In a graph, we would just have these nice curvy isoquants that are parallel, never crossing, downward sloping, and never cross the axis. Look at that. So good. Next, let's think about the kind of problems that firms solve. What are the firm's goal? Remember, consumers can either maximize their utility or minimize their expenditure. Answer for yourself what two things a firm might try to do. Hopefully you thought that firms might minimize the cost of their production subject to making a certain amount of stuff. That is similar to a consumer minimizing their expenditure. Firms alternately might maximize their output subject to cost, which is similar to a consumer maximizing their utility subject to some budget. So let's assume we have Cobb-Douglas production. We saw before that will give us curvy isoquants. We also saw that given linear pricing of our labor and capital, we'd have straight linear ISO costs. Let's say I wanted to minimize my cost subject to being on this isoquant. What combination of labor and capital would I choose? Well, clearly I'm going to want the tangency. Answer for us why the tangency is the right point, right? Why do I want this combination of goods, not this one, not this one? Well, it must be that any point other than this is either insufficient or inefficient. So let's first talk about the insufficient combinations. Obviously, this bundle of L and K is much cheaper than this bundle, right? This is a better job of minimizing costs. However, it's insufficient. We don't make enough stuff. So we know that anything below this purple line is not good enough. Next, we might look at anything above this purple line. Well, if you pick any line above this purple line, I can find you a point that is strictly cheaper, i.e. this point is strictly cheaper than this point. This point is strictly cheaper than this point. So it can't be those. So then let's look only on points on this purple line. The cheapest one is going to be here. To check that, if I pick any other point on this line, I can find a cheaper point by heading along this isoquant towards the tangency point. The tangency point, the single highest crossing, is going to be the most efficient means of production. So graphically, just like we did the consumer problem, look for the tangency that gives us efficient and sufficient production. Next, mathematically, how would I minimize cost? Think back to utility maximization and expenditure minimization. Use the same techniques. The first way we do is what we just did, the lowest ISO cost rule. If we have some isoquants, we want to find the most efficient way to produce this, look at all the ISO costs and find the lowest one, the one that's tangent. The other thing you might have thought of is what we call the tangency rule. This is just saying that when we have an isoquant and we have an isocost, if they're tangent, they will be the highest crossing, lowest crossing, right? These are going to be the same. One we have not explicitly discussed before is number 3, and that's called the last dollar rule. If you are producing optimally, your dQdL divided by the price of L, i.e. W, will be the same as your dQdK divided by your price of K, which is R. Although we didn't explicitly talk about this for the consumer's problem, it's fairly obvious, right? We talked about looking at mu1 over p1 and how that compares to mu2 over p2. Obviously, if you rearrange this function, you'll get this function. So these are saying the same thing. Next, suppose now we want to minimize costs subject to our production function being greater than some q. What are our choice variables? What function are we maximizing, and what is our constraint? Answer that one. Then, what is our first order conditions? So first off, you'll note we are maximizing, or minimizing actually, our expenditure, I mean our cost. So this is our function. How much should we spend? Make that as small as possible. What's our constraint? Well, we said that the total output must be at least Q bar. So that means at optimal, Q will equal Q bar. So it seems like we are minimize cost subject to sufficient quantities. How would we find our first order conditions? Well, as before, we're just going to take the derivative of our Lagrange function with respect to the 3 choice variables. You're going to find that W equals lambda times df dl, R equals lambda times df dk, and that our constraint must be obeyed. What would you do now? Let's say you have these 3 FOCs. How would you solve this? Obviously, we could rearrange them by setting these 2 equal through the lambda term. If you do that, you're going to find W over R equals MPL over MPK. Does this function look vaguely familiar? What did we find when we did the consumer problem? See if you can remember. You'll note that W over R equals MPL over MPK. That is the tendency rule. And this is the same as what we did in consumers when we said that MRS equals MRT. MPL over MPK refers to moving along the isoquant. That is the MRS-like object for producers. And W over R is our price ratio, which is the MRT-like object for producers. So if we were to Lagrange it out, you'd find we have to obey the first of the rules we just suggested would solve our production. Next, how did things change? Well, let's look at this graph. Imagine that labor became cheaper. How would our graph change? Well, you'll note if labor became cheaper, the quantity of labor we could buy, if we bought only labor, it would go up. And if we compensated ourselves to remain on the isoquant, like we did when we were doing the compensating differentials kind of stuff, we could also assume that, hey, maybe our capital got more expensive too, right? And if we make labor relatively cheaper, you'll note that we move along the isoquant to a labor to capital ratio that is higher. So all the same types of intuition we built doing the consumer problem, all the same tricks happen here. Again, the only difference is we're looking at labor and capital, not good one, good two. What if we want to increase production? How could we find an optimal bundle of labor and capital subject to some higher quantity? Well, if I wanted to find that, I'd draw higher iso costs and higher iso quants. If I did this, we'd find what's called an expansion path. Basically, we'd have this ray finding all of the tendencies going up through space away from the origin. And the interesting thing about this is, although this one's straight, it could take any path, right? It depends upon your production function and how your returns are in terms of scaling up labor and capital. So now it's time for y'all's practice. First, assume we have Cobbs-Douglas production. Let the prices of labor and capital be given, and suppose you need to make 100 units of output. 1, what's the cheapest way to make all 150 units? And 2, what changes if we have to make 150 units instead? Then, repeat this process, assuming you have the same production function, same costs, but suppose you have to make 200 units, and then 250 units. Let me know how it turns out, and I'll see you next time. Bye.